Welcome to our final example in this series on unsteady heat transfer. Today we'll analyze a practical scenario involving a cylindrical ingot undergoing heat treatment in a furnace. This problem requires us to determine the optimal speed at which the ingot should move to achieve a desired temperature, a critical aspect in industrial processes. Let's look at the problem. A cylindrical ingot, 10 centimeters in diameter and 30 centimeters long, is passing through a 6-meter long heat treatment furnace. The ingot must reach a temperature of 800 degrees Celsius before it exits the furnace. The furnace gas is at 1250 degrees Celsius and the ingot's initial temperature is 90 degrees. We need to find the maximum speed at which the ingot should move to attain this required temperature. We are given a combined radiative and convective heat surface transfer coefficient H of 100 watts per meter squared degree Celsius. The thermal conductivity of steel K is 40 watts per meter degree Celsius, and the thermal diffusivity of steel alpha is 1.16 times 10 to the power minus 5 meters squared per second. Let's begin by setting up our solution. We list the given parameters and ensure all units are consistent. The diameter D is 10 centimeters. The length L is 30 centimeters. The initial temperature of the furnace gas, Ti, is 1250 degrees Celsius. The target temperature for the ingot, T, is 800 degrees Celsius. The ingot's initial temperature, Ta, is 90 degrees Celsius. Thermal conductivity, K, is 40 watts per meter degree Celsius. The heat transfer coefficient, H, is 100 watts per square meter degree Celsius, and the thermal diffusivity, alpha, is 1.16 times 10 to the power minus 5 meters squared per second. Next, we'll calculate the characteristic length, LC, for the cylindrical ingot. Now, for a cylinder, LC is given by the ratio of its volume to surface area. This simplifies as shown. And plugging in the diameter and length, we find LC to be approximately 0.02143 meters. Now, we calculate the Biot number, BI, using the formula HLC over K, and we get the Biot number to be equal to 0.0536. Now, since the Biot number is less than 0.1, we can confidently neglect the internal thermal resistance of the ingot for conduction heat flow. This allows us to use the lumped capacitance method, which simplifies our analysis significantly. Now, the time versus temperature relation for lumped capacitance method is given as shown on the screen. Now, let's simplify the exponent term in the time versus temperature relation, and we do that. We plug in the thermal diffusivity, the heat transfer coefficient H, thermal conductivity K, and the characteristic length. Plugging in the values, we find that the exponent term is equal to 0.001353. Now, when we substitute back into the time temperature relation, we have the equation as shown, and this can simplify further to the left hand side having 0.612 and the right hand side equals to exponent 0.001353 tau. And from this, after taking logarithms to both sides, we find that the time tau will be approximately equal to 362.9 seconds. Finally, to determine the maximum speed with which the ingot should move, we divide the furnace length by the calculated time, and the furnace length is 6 meters and the time is 362.9 seconds. Thus, the maximum velocity v is equals to 0.01653 meters per second, and that is our answer. Thanks for watching. If you found this video helpful, please consider subscribing to our channel for more content like this. Don't forget to hit the notification bell so you don't miss out on any of our latest uploads.